Hey everyone, today's topic is logarithmic functions and graphs. What we're going to learn is how to convert between exponential equations and log equations. We're going to find common logs and natural logs with and without our calculator. We're going to change log bases and we're going to graph log functions. What I want to start this lesson off with is a comparison between exponential equation and a log equation. A lot of students get scared by the word logarithm. They think, oh my God, I can't do logs. Yes, you can. It's very, very easy. It comes down to this very, very easy, very simple explanation. An exponential equation is such like this. 2 to the third is equal to 8. We all understand that. That makes sense. This same equation written in log form looks like this. Basically, a logarithm is an exponent. So this is saying when the base is 2 and the answer is 8, 3 is the exponent. Look at these examples. 2 to the third equals 8. 2 to the third equals 8. This is the same expression written in log form. Listen to how I said that. Log base 2 of 8 is 3. Practice saying it correctly. Don't say silly things in your head. Make sure you're saying it correctly. Use the correct language. It's going to help you. Okay. Now, what I want you to do is convert the next 4 examples. 2 of them are exponential equations. You want to write those in log form and take expressions that are in log form and write those in exponential form. If you feel like you're confident and you're ready to go, pause the screencast and see if you get it. The rest of you can hang on and I'll give you a little bit of a hint. So a to the b is equal to c. What you're going to do here is identify the base. It's going to be log base A. What it's equal to is C. So log base A of C, and that's going to be equal to the exponent, which is B. Give it a shot. These are the answers. Log base A of C equals B. In this problem, we had the log equation. We had to write it in exponential form. So it's 2k to the 9th is equal to m. Here we have log base e of 72 equals t. And in this last one, it's written backwards, but we know what to do. It's 5 to the x is equal to m. Excellent. Okay, let's continue. So what we want to do is use this definition of logarithms to find some logarithmic values. Here's the first 3 I want you to try. The log base 4 of 64, the log base 3 of 81, and the log base 2 of 1/16. So basically what we're being asked is 4 to what power gives us 64? And on this one, 3 to what power gives us 81? And on the last one, 2 to what power gives us 1/16? Well, 4 to the third power is 64. 3 to the fourth power is 81. Now, how am I going to get 1/16? If you know your laws of exponents, you know if I start with 2 and end up with 1/16, I must have raised 2 to a negative power. So 2 to what power gives me 16? And that would be 4. So the answers are 3, 4 to the third is 64, 4, because 3 to the fourth is 81, and negative 4. Why the negative sign? Because that's what makes it 1/16. Do those make sense? I hope so. Let's look at another few examples. Here I've given you 4 examples. So the first one is the log base 10 of 0.01 or 1/100th, the log base 7 of 7, the log base 4 of 1, and the log base 8 of 2. I always like to convert those to an exponential equation. It helps me to understand what I'm being asked. So this is saying 10 to what power is equal to 0.01? And 0.01, remember, is 100th. I'm thinking I'm going to get a negative exponent here, right? 7 to what power is going to be equal to 7? Well, I ended up with the same number. Seems like this should be 1. 4 to what power equals 1? This is a little tricky, but think about that. 4 to what power is going to give me 1? Well, that's looking like 0 because anything raised to the 0 power is equal to 1. This one is a little tricky because we have 8 to what power is equal to 2. So, I started with 8 and ended up with 2. Not sure if you would have seen this right off the bat, but this is going to be a root. So it's the third root. So this answer is going to be 1/3. Here are the answers. Okay, the next thing I want to do is I want to talk about how we're going to do these logarithms on our calculators. So here are two questions I want you to figure out. The log of 5 and the natural log of 3.9. So I have the face of your calculator on this screen. And there are two buttons on this calculator on the face that have to do with logarithms. The first one is this button right here labeled log. That is the same as log base 10. And the second button is this LN. I have had students in the past think that says IN. It doesn't. It says LN. L as in lollipop. So LN is the log base E. So if you want to use those, you can use those to find the log of 5 and the natural log of 3.9. This is called the common log, and this is called the natural log. So the common log of 5, log base 10 of 5, is approximately 0.699. And the natural log of 3.9 is approximately 1.361. Okay, common logs and natural logs is what we just talked about there. So the next thing we're talking about is a problem like this. So just like I did before, I am asking you to use your definitions of logarithms to find these values. What's the log base 7 of 35? Well, 7 to what power is equal to 35? I have no idea. That's going to be a decimal. That's not one I can do in my head like the previous examples that I showed you. So what are we going to do? Well, luckily and lucky for you, there's something called the change of base formula. And the change of base formula says that we can make the base anything we want. So if we have the log base b of m, it can be equal to the log base a of m over the log base a of b. What you want to notice here is the base here is b, right? And that's the base in our change of base formula. And the log base b of m is the log base a of m is on top. So if we're going to do that with this problem right here, this log base 7 of 35, we're going to use the change of base formula. Then I'm going to write the log base a of 35 on top, and I'm going to write the log base a of 7 on the bottom. Now, I'm allowed to use whatever base I want. What base do you want to use? Personally, I want to use the ones that are on the calculator. So I'm going to use either the log button or the natural log button. I did it both ways for this problem, and you'll notice I end up with the exact same answer, and that answer is approximately 1.83 or 1.827. Okay, now switching gears again. We're going to switch gears to these exponential and logarithmic graphs. So we've already graphed this equation, y is equal to 2 to the x. If you'll remember, we plugged in some values and we got these answers. We did this in a previous screencast and we know what this function looks like graphed. Check this out. X is equal to 2 to the y. See how I switched x and y? Isn't that the definition of inverse, right? So think about a table of values that would work here. So in this problem, when I plug a -2 in for y, I get 1/4 for x. Do you see how the domains and ranges switched? Definition of inverse. Look at the graph. Notice that this graph is also the inverse of y equals 2 to the x. That should all make sense. Remember, it's a reflection over y equals x. Well, this equation over here on the right, how would this look in log form? Remember, we did this in a couple screens ago. Change this exponential equation to a log equation. Well, written as a log equation, it's going to be the log base 2 of x equals y. And there you have a log equation. This log equation is the inverse of this exponential equation. Kind of cool, right? Let's explore this log equation just a little bit more. All of this should be making sense and falling into place. We know what the graph looks like. We have a table of values. Now, what's the domain of this function? Well, the domain of this function, it goes from 0 to infinity. See, the log base 2 of x. X is that number that when you raise 2 to something, you get this number. Can you get 0 here? No, it's undefined there. So the domain goes from 0 to infinity. And doesn't that make sense? Because that's the range of the exponential function. And the range of this function is all real numbers. Y can be anything. And instead of a horizontal asymptote, we have a vertical asymptote, and that's at x equals 0. One last example in this screencast. So we have this new function that is equal to the log base 2 of x minus 4. Now use what you know. You know a lot. You're doing well in this class. So what does that -4 do to the graph? You knew it, right? It's moving it to the right 4 places. The blue graph is the log base 2 of x. The red graph is the log base 2 of x minus 4. And it's shifted to the right 4. The domain of this function is 4 to infinity, not including 4, because remember, this cannot be 0. This can't even be negative, because there's no power you can raise 2 to get something 0 or negative. The range, all real numbers, and this has a vertical asymptote at 4. I'm going to record a really quick screencast that's going to help you using your change of base formula on your calculator. Be sure to watch it. Email me with any of your questions.